Yeah, hey everyone, thanks for coming to this talk. Like he said, there's a break after this, so just try and muster as much energy to kind of get through the next 30 minutes. So my talk is going to be on Rust's memory model, specifically looking at the atomic section of the memory model. We know concurrency is a hard thing, and I kind of want to find a way to bridge the gap onto how to explain these things. You know, I started off not knowing it, but I've gotten pretty far. And it's also very complicated at the same time. So bear with me, but I've done my best to make sure everything is correct as possible. So a little bit about me. I am a senior backend engineer. I was previously at GoDaddy after just relocating. And I did my master's in computer science in evolutionary algorithms. How many of you guys know what that is, evolutionary algorithms, genetic algorithms, stuff like that? Okay, great. So I started with that. I realized, hey, you need a lot of concurrency for this kind of stuff, a lot of parallelism. You know, you have a lot of individuals that are interacting, and you need to be able to have them recombine in a way that is correct at the end of the day for you to see your programs work. That's my LinkedIn. Email me at rust@Ombura Jr. I am currently freelancing, but also looking for more permanent positions as well. So at a high level, my talk's going to cover like the 10,000-foot view. How do we get to this point with all the concurrency issues we seem to have? We look at Rust's atomic memory model and how that borrows from C++ and C. We look at some of the key theory that will underpin a lot of the things I end up talking about after. So memory ordering options, as well as some of the patterns and examples at the end. It's a tough topic to try and condense into 30 minutes, so I'll give it a shot. All right, so here we have an image, and it's an image you guys have seen a lot. I've gotten this one from one of Apple's patents. And you know, CPUs trying to connect to some form of shared cache or main memory. On the far right side, you have the internals of a CPU. A lot of these micro components are part of the micro architecture that some of those components we may be familiar with. A lot of that exists to keep that pipeline moving in the CPU. You know, all of us are out here, whenever like a new CPU comes out, we want that extra gigahertz of performance or whatever it is. We're watching like Linus Tech Tips for just like, hey, can I eke out a little bit more? Can I overclock? Hardware designers have had to ensure that, hey, to enable that, we have to have a lot of those components in there, but it also adds to the complexity. At a higher level, the compiler is also doing things to make things simple. I got this straight from the sync module documentation, and all it's doing is it's taking a somewhat poorly written app and doing a lot of optimizations to it, and basically outputting print 744. So the compiler is smart enough to be able to perform those optimizations, get rid of code that's not required, and then change the code. This is great for us because our code goes from being potentially slow to pretty fast given those optimizations. But we'll see in a second that actually poses some problems when you start to think of, okay, what's happening with multiple cores when certain data is being removed by the compiler or being reshuffled or being reordered. I like that quote at the bottom. The compiler knows what you said, but not what you meant, right? And so you have to tell it, hey, this is exactly what I want to happen. It can't infer meaning from you, otherwise the compiler might be doing a bit too much. All right, so let's look at an example of program execution. We still have that single core there. I got this off the ARM website, and I think it's a pretty good one that illustrates what's going on. Don't worry if you can't read ARM. We have 3 instructions, a store, a load, and a load, all tagged access 1, access 2, and then access 3. The first one will attempt to store some data in a register into memory. The second one will attempt to load from the stack pointer and then post increment by 4, and the third will read from some register. So one of the possible execution scenarios that we end up having is your access 1 performs a write, but instead of pushing it all the way to main memory, we're going to keep it a store buffer, right? It's a lot simpler for me to keep this bottle here instead of me having to take it back to the kitchen, right? I can do that later while I work on other things. Access 2 might perform a read on the stack pointer, but that could cause a cache miss. So I actually have to go fetch the actual address. And access 3 performs a read that hits. So what ends up happening internally is that you have access 3 completing first, because the data is already there, access 2 having to come back from memory with data from about the stack pointer, and then access 1. So we have this out-of-order execution scenario that happens internally within a CPU. And that's fine in a single-threaded environment, because as we'll see in a second, in a single-threaded environment, everything retires in program order. They may execute out of order, but they retire back in program order. So when you write our apps, we don't have to think about, oh, is this going to be executed before something else? No, that's all handled by the architecture. So ARM, x86, basically most architectures do this. Now, in a multi-thread execution environment, things get a bit weird. When access, for instance, what we may end up seeing is this interleaving of operations. And other cores might take those out-of-order operations and start to work on them and giving you these false outcomes or this weird outcomes as we're used to. And that can cause data races, viewing or working on stale data causes a lot of problems. And so one of the ways Rust attempts to do this is by introducing an atomic memory model that attempts to solve this. There are other ways of doing this, but I'm going to focus more so on the atomic perspective today. So Rust basically borrows from C++. And the reason, as we'll see in a second, I have a lot of slides, so I'll kind of be going through them pretty quick, but I'll post the slides later. The reason Rust does this is it's pretty difficult. The Nomicon just straight up says, like, yo, listen, this is hard, all right? C++ has done this right. We're going to copy from them. And the things that don't apply to Rust, you'll see later, a particular type of ordering has not made its way to Rust for good reason. We're not going to deal with that. We'll just take all the good parts, right? Hey, there's nothing wrong with that, right? And so it even says at the bottom there, like trying to explain this model, and it is fairly hopeless, right? And so I kind of look like a fool standing here trying to explain this thing that even the documenters of this have said, hey, it's pretty hopeless. But we have to do something at the end of the day, right? We have multiple cores. We need to write consistent and correct programs. So what's an atomic variable, right? An atomic variable is a memory location that language and hardware treat as a single indivisible unit for a specific set of operations, for a specific operation. And atomic types provide this primitive shared memory communication between threads, and they're the building blocks for other concurrent types. So you guys may have heard of mutexes. A lot of those will use some of these atomic semantics underneath the scenes, the read-writer locks, all those other things. We'll look at channels later on, and we'll see how these actually interact. Rust exposes a given set of atomic variables on the right over there. So you have your Boolean types, your integer types, your pointer types, as well as if you're running nightly, you get access to the I28 and U28 if you're about that life. But I'm a bit more conservative, so I wouldn't really play with those. These atomic variables also carry with them certain characteristics. When it comes to usage, it makes sense that they implement both send and sync because we need to use them within threads. However, they still follow the Rust threading model. So if you're going to use them within threads, it's either you wrap them within an arc or have them be statically available via some form of lazy global initialization. From a portability perspective, what we see is that all atomics are guaranteed to be lock-free if the hardware makes that available. What that means at the end of the day is that there's no internal mutex that they try and lock onto and then hold such that it does its operation then release. Atomics, on the other hand, are not guaranteed to be weight-free. So what does that mean? It means that some of these operations that we'll see in a second, like fetch or the compare exchange, may implement loops underneath the scenes. So they're lock-free, but not weight-free. That distinction is important, especially when you're looking for performance. All atomic variables take some form of ordering. So when you have atomic, it's just in memory, you just have a string of bytes, right? There's nothing special about atomics. It's when you start to apply these orderings to them, you start to inform the compiler, hey, you can't reorder these atomics in a way that may cause confusion. And the hardware treats them very special. And so when we apply an ordering, we start to tell the underlying system, hey, treat this memory region as important. And the cache coherence system that we'll see in a second treats them important and ensures that when invalidations happen or visibility needs to happen, it's done correctly. Lastly, from a hardware restriction perspective, atomics are naturally aligned. So if you have an atomic I64, it's aligned by 8 bytes. And they're not supposed to straddle cache lines. And this is more so a performance thing. So the way that cache coherence works, it works with the notion of cache lines. When a cache line is pulled down, it's worked on, maybe some modifications are done, and then it's kind of pushed back into the coherence system. CPU doesn't just pull a single byte or a set of bytes that you want to work on. It brings the whole thing down. Cache lines typically tend to be like 64 bytes, depending on architecture. Now, if you have an atomic that straddles 2 cache lines, maybe it's in that point right in the middle, how do you have an atomic operation when I have to pull down 1 cache line, change up those bits, then pull down another cache line, change those bits, when another core could be doing modifications to that, right? So some architectures allow it, it just becomes a performance hit, because now you're asking for 2 cache lines when the other CPUs can't do anything with them. Another thing is to avoid this idea of false sharing. So This is another performance thing that I think is important to know. If you have atomics on the same cache line, let's say atomic A and B, let's say they're 8 bytes or whatever it is. Let's say you have two threads. One thread wants to modify A, another thread wants to modify B. And maybe they're doing a lot of operations on these ones. If they're on the same cache line, they'll keep having to be pushed, go back and forth, back and forth, back and forth, and that creates a problem, at least performance-wise. It'll still work, but you'll start to see a lot of degradation. And then lastly, that whenever you're working with atomics, if you have like an atomic U16, you can't attempt to change part of that U16. Maybe you just want the last eight bytes or whatever it is, or half of it to modify, maybe set it to 0. Doing that causes UB because you're no longer accessing it atomically. You're now accessing using some form of overlapping memory. And in C++ and Rust, that is not allowed. So where does this idea of atomicity come from, right? A lot of it's, or at least a lot of it's implemented within the hardware. This within what's known as the cache coherence subsystem or cache coherence or the coherence microarchitecture. This may exist within your cache lines or your L1, L2 caches, sometimes within the CPU, depending on architecture. And what this does is that it ensures that atomic operations execute, that they acquire ownership of a cache line, and using this coherence protocol, and their effects become visible to other cores via cache-to-cache transfers. On the right, you can see an image of what a cache line state might be in. I took that image from I think it's AMD documentation. A particular cache line could be in an invalidated state, owned, shared, and those arrows show transitions that that cache line can go into. So if one cache line is brought in, others have to wait. If I modify some value, I have exclusive access to that cache line. All the other CPUs that have a reference, have a copy of that cache line, need to invalidate that. And this is how we create a coherence and consistency throughout the system. And some of the protocols are like MESI and MOASI. They've been around since the 80s, if I'm not mistaken. All right, so let's talk about a bit of memory ordering theory. Sorry if this begins to sound like a lecture, but I think these concepts are very important to kind of pin down before we move forward. So a lot of these, again, come from the CPP reference. Rust still uses them. They might use different words or might not even allude to them, but it's important to kind of have them if you want to deal with these things at a more advanced level. So sequence before basically means that you're following strict program order or operand evaluation. What does that mean? It means that if you have like some operation A followed by B, A sequence before B. You can just think of it you can just think of it in a way that A just happens before B, as what you've written in program order. Modification order, which I think is even more important, talks about how an atomic variable change throughout the course of the execution within a program. So if you have stores to that atomic variable, how do those stores interact with atomic, and what values are you seeing along that chain? Synchronizes with, here we start to look at how threads that use a shared atomic synchronize with each other. This is a precursor to happens before, which is next. And so for synchronizes with, if an atomic store in A is a release operation, and we'll talk about what release means, on X, and an atomic load on B is an acquire operation on X, and the acquire load in B reads the value in the release store written by A, then we can now say that A and B have both synchronized. Lastly, we have happens before. There's intra-thread happens before, and inter-thread. I hate those words, even though they mean very different things, but sound the same thing. Sound exactly the same. Intra just means within a single thread. What does happens before means? It's basically sequence before. If you have some operation A, then B, A happens before B. Within other threads, that's when we start talking about this notion of synchronizes with. And we'll use that in a second. So let's look at modification order. I have a few diagrams I'm going to show you about how a particular variable can move. But just to redefine it, so modification order cares about how an atomic's value changes over time. So if I'm applying X, some atomic X, and storing 1, 2, 3, I expect to see 1, 2, 3 as the linear modification order to it. Now, in order to kind of ensure this happens, we need to tell the compiler that, because the compiler wants to reorder things. If it sees that, hey, we need to do some load later on, I'm going to hoist that earlier into the program so that that load can be pulled from the cache earlier on. A lot of these optimizations are great, but when it comes to multi-thread scenario, it can be problematic. And so these coherence requirements, these four ones that are write, read, read, and read, write, they constrain the compiler the moment you start working with atomics. And the hardware knows exactly what to do the moment it sees that. So one of them is write coherence. A lot of these are very basic to understand, very simple. We have some code up there, single-threaded and multi-threaded. And all they're doing is just storing variable to x, which is the atomic 42 and then 100. And so write coherence just says if write W1 to some atomic x happens before write W2 to that same atomic, then write W1 is earlier than write W2 in its modification order. It's kind of obvious, right? We're just kind of stating the obvious. But it's important the compiler knows this so that it doesn't do certain things like this, where it swaps having W2 first and then W1. So on the left, you have the thread. On the right, you have a swim lane for the actual atomic and how it's being modified. We shouldn't see 100 appear first before 42. Instead, we should have a scenario where that sequence order is obeyed, and write 1 happens first and write 2 happens second. In a multi-threaded scenario, what we have now is threads can execute whenever they want. So it's possible to have write 1 go first, change x, write 2 go next, change x, and then if you're to read x after, we should expect to see 100. Once again, threads can execute however they want. Thread 2 can start, go 100, and then 42. So in a multi-threaded scenario, this is valid. Read says basically the same thing. If a read R1 on atomic x happens before a read R2 on x, and R1 took its value from a previous write W1 on x, then we expect that R2 should either read what W1 wrote, or if there was another write that came between R1 and R2 should be able to see that. This is where things get interesting. Single-threaded, this is what we expect. Write 1 happens first, it writes 42. Fine, we know that. Read 1 comes and reads 42, and read 2 comes and also reads 42. This is what we expect, right? Single atomic, we expect read coherence to be obeyed. On the right, you can see that little table of outcomes. We can't expect either value to be 0. Why? Because there's a write to that atomic in a single thread, and we expect that to be seen by all the subsequent reads. Similarly, we can't expect one to read 42, another to read 0, or any interleaving of those two. In a general case where you can now have another thread come in and do the write, you have interleavings that can happen between the writes and the reads that now make other outcomes possible. So when you're debugging and now you're adding threads, you now realize like, oh, there are more outcomes that you need to kind of care about. And if you're following the modification order and you understand some of these definitions that I've given earlier, you can now start to understand how these outcomes may come into place, and more importantly, what outcomes are not allowed. Like in this case, 42 and 0 is not allowed. And why is that the case? Well, for R1 to read 42, we know that the store has to come in, R1 reads 42, and then R2 reads the previous value, which can make sense. We said if you read coherence, if your previous read has read 42, R2 has to read 42 now. All right, and then there's read-write coherence. We've kind of gone through a little bit of this. It kind of states like some of the intermediate states as well, and then there's write-read coherence as well. All right, so let's talk about memory ordering itself. Like I said, memory ordering applies to the atomic, and it tells the compiler and tells the hardware how should this atomic behave, not just with itself, but other operations around it. And the Rust provides the 5 sets of ordering. This enum in Rust is actually not non-exhaustive, and that's why it's an evolving field. We might find more orderings that make sense later on. This is like and if you look at the history of how these have actually come about, I think sequential consistency was the first, and then more relaxed orderings kind of followed after. And a lot of programming languages had to change their memory models to accommodate these. So in general, when you start off with relaxed, you typically have more hardware-friendly code being released. The compiler and the hardware knows I can do a lot more optimizations with this, so long as I ensure that relaxed ordering is followed. With acquire release, that is our bread and butter for synchronization, and I'll talk about those in a second. And then with sequential consistency, we kind of come back and allow the programmer to, quote unquote, be able to more easily reason about the code that they're writing, because everything is sequentially consistent. Now, I think sequential consistency is also pretty tough, but we'll see why in a second. So what does relaxed ordering guarantee? So when relaxed ordering is applied to some atomic, it does not do any synchronization, but it just ensures atomicity, right? And so that's why it's typically used for counters. If maybe you have some statistics application, and a lot of threads need to write and update a counter, you're going to get atomic write updates to that atomic, so long as you're using relaxed ordering. And so however, mixing relaxed atomic operations with unsynchronized non-atomic accesses can also lead to data races. So if I have atomic stores that are going to a particular atomic, and I choose at some point, no, I'm just going to get a raw pointer to this, and I'm going to mutate this. UB, automatic. That goes without saying. So let's look at this code right now. Just take like 20 seconds to just try and see what's happening, and we'll kind of go through some of the outcomes of what this code could mean from a modification order perspective. So we have two atomics here, X and Y. Each of them are, and with two threads that are running. R1, W1, operation R1, W1, R2, W2 in either thread. And in thread 1, we're loading from Y into R1, and then we're storing R1 into X. Then in thread 2, we're gonna load X into R2, and then we're just gonna write 42 because we can. All right, so let's see what happens from a modification order perspective. Now we have two swim lanes because we have two atomics, right? And so this is a general example of what could happen. Those arrows can show any form of interleaving between the operations. What's important to notice is what's happening on either thread. If you look at the code and you look at what's happening in R1, there's a data dependency there. R1 is loading from Y, but X needs the outcome of R1 in order to store that. And so that data dependency enforces that sequence before happening. So what that means is W1 can never happen before R1 because it needs that data. On thread 2, these are two operations happening on two separate atomics. The compiler, and the hardware can choose to run them however it chooses. And so it can interleave them. So we kind of get a very interesting outcome here. And I'll just run through them because there are quite a few. In this first case, and now this arrow on the left shows that you can now follow each arrow as a timeline. So R1 happens first, W1 happens second, R2 happens third, W2 happens fourth. And that outcome, and those are the outcomes we expect at the bottom, 0, 0, 0, 42. Now, if you have a different ordering, so R1, R2, W1, W2, same thing. Different one, same thing. Different one, same thing. Different one, same thing as well. All right, now we have an interesting one. When W2 actually writes before any of the stuff that happens in thread 1, we start to see 42s appear a bit more. Same thing with case 7. The W2 is now been swapped with, and that's what the red I highlighted in the text there. W2 is actually now being swapped with R2 because remember, there's no interdependency between the two, and so it's possible for them to be interleaved. So W2 happens first, R2 happens second, and then R1, W1. So we start to see 42s. Similar thing there, a bit more interleaving. And then we have a situation where everything's 42. All right, so if you run this kind of program, you're gonna get these outcomes. More likely to get a lot of the zeros, but in one of those cases, you'll probably see a lot of this as well. And so it's a table just outlining everything there, summary. So that's relaxed ordering. With acquire ordering, this is almost used in tandem with release. So acquire is usually used whenever you're trying to load something with load operations, and acts as a barrier that prevents instructions that come after it from being hoisted above it. Remember the ordering the compiler can do? Compiler sees you're using acquire, oh, I can't push above this boundary. And this image from the ARM website, I think really shows that really well. So the LDA instruction is that load acquire, and it prevents everything below it from being hoisted above it. But anything above it can still go below it. And so it's paired really well with the release ordering that does the exact opposite. Everything above it can't go below it. Everything below it can go past above it. And when you combine this acquire and release ordering, you end up getting your critical code section. So whenever a mutex is used and you have a quote unquote the critical code section that we're used to having, that's exactly what's happening. These two atomic orderings are creating that section by preventing code on either side of them from being hoisted above and below them, and also creating a section where everything that code cannot go past them. I forgot to mention, when you do a release, all the code that happens before it gets flushed now into memory. So the other threads can now see that outcome. Yeah, you also have a hybrid one that uses both of them, especially not methods that can only take one ordering, but you need that acquire release kind of synchronization. And then you have sequential consistency. So in sequential consistency, each thread kind of creates, each thread's execution creates this global order, which is typically called S. And so this means that in each concrete run, there must exist a single total order S over all sequentially consistent operations. This includes every single variable that uses sequential consistency. You now have this global order. S must also be consistent with atomic modification order and happens before, which we talked about earlier. And there's also this notion of strongly happens before, which was introduced later into the C++ spec, and Rust obviously just also acquires it, that kind of hardens sequential consistency. Now, the reason I think sequential consistency, say that 10 times real quick, it's not easy. The reason sequential consistency, I think, is difficult is because it requires a lot of things to happen right for the hardware to start executing in a manner that is sequential consistent. Remember, this is not how the hardware is meant to operate in general, right? And so this total order that I was talking about, S, if you have an operation A, B, C, D, where A happens before B and C happens before D, the total order, the single total order, is any permutation of those 6 outcomes. So when you run the application or your code 6 different times, you may observe these 6 global orders. All of them are valid, right? And so the idea is not to eliminate all of them and have one. The idea is to, like, your hardware is still allowed to move things around, but in a manner that makes sense in a sequential consistent way. So notice how A and B, in those 6 orders, B never overlaps A and C never overlaps D. That's why we have those 6 different outcomes. So like I said earlier, there are problems with this. It's very hard to ensure. And what some of the guys who are writing the C++ spec realized, actually academics, shout out to academics, they realized this, was like for certain hardware, everything I've just said does not hold. And this is why this strongly happens before had to be created in order to ensure, in certain cases, sorry, I think I'll just leave that there. That in certain cases, sequential consistency needs to happen as expected. So let's look at an example here on the left. So here's some code here. I'll give you like 20 seconds just to kind of look at it. But we have sequential consistent store on X, and a release on Y, meaning Y can now, once Y is released, everything above it gets released, meaning if there's an acquire somewhere, it will read that, or if there's sequential consistency ordering, it will also read that. Thread 2 does the same thing. We're also using sequential consistency and relax there on the fetch, add, and load. And then thread 3, we're spawning a thread that stores 3 to Y, and it loads using sequential consistency to R3. This is allowed to produce a weird scenario where R1 is equal to 1, R2 is equal to 3, and R3 is equal to 0. So in your head, you can just take some time to kind of figure out how do you get to that. But basically, what we're realizing is when you pair sequential consistency in a manner with which you're also using other orderings that are weaker with it, you start to violate some of the guarantees sequential consistency actually gives. And so when you look at some of the examples that I'll show you later, if you're going to use a sequential consistency, particularly for stores, you have to be consistent with it throughout the choice of your application, and for that atomic as well. All right, so last I'll just go quickly through some of the atomic methods. There's some plain operations, the load and stores, and then the read modifier writes. So the conditional ones and unconditional ones. So the plain ones, load and stores, we've seen a lot of these. No need to explain those. And for unconditional read modifier writes, we have the swaps. So all these apply to atomics, by the way. Swap, these are unconditional, meaning they always succeed. So if you ask for a swap, hey, take this, swap it with that, that will always work. Same thing with fetch add, fetch sub. It will, like fetch add, it could add a value to it. That will always work. We'll take the existing value, add a value to it, give you the old value back, and now the new value exists in memory. Now the conditional ones, like the compare exchanges, which are pretty popular, you have the value self. So let's say it's AtomicUsize. You have self. If self is equal to current, then push in this new value, right? And if that works, we're going to use a particular ordering for that success condition. If self does not equal to current, we're now in a failure scenario, and we have to use a specific ordering for the failure scenario. So there's certain orderings that can only be paired with a success condition, and certain orderings that can only be paired with the failure condition. There's also the compare exchange weak variant, and this was created because certain architectures, like ARM, your weaker architectures from a memory model perspective, they can hit a scenario where if self is equal to current, it fails. So you're wondering, how is that even possible? They're equal, right? Shouldn't that exchange happen? Well, within the microarchitecture, I guess, of how ARM is implemented, if those are equal, kind of like how, I think the best example I can give is whenever you're trying to write to a database, a pretty big transaction, and you give it a timeout. at any point, if that transaction does not complete, the entire operation can fail, even though nothing went wrong, particularly with those transactions. So same thing, the core is asking for some information that a different thread holds onto. It sees that they're equal, but the timeout, maybe that thread's doing a lot of work on that cache line, it ends up timing out, and even though they're equal, it failed. And so the way you kind of go about this is just put this in a loop. You'll see this pattern used a lot, and then the next iteration, it'll probably work, and you're good to go. So I don't know if you guys work on ARM, but man, I don't know what they do, man. Like they do a lot of stuff there, and but it works. At the end of the day, it works well. And so here's just a list of I got from Wikipedia some of the stronger architectures and the weaker ones. And the way to kind of figure that out is the first column shows you what type of ordering it allows. So you have your loads can be ordered with stores, loads can be ordered with stores, loads can be ordered with after stores, stores can be ordered after stores, blah blah blah, all the way down. Your weaker orderings, or weaker architectures, technically, are all the ones with the Y next to it. They allow that type of reordering to happen. Your stronger ones, your x86s and AMDs, have very few yeses next to them. And so they typically will execute a lot of the instructions in a manner that actually is more intuitive to us. All right, so I'm going to quickly go through these last two examples before I close out. So this one is the one-shot lock. I got this from Mara's book. Have you guys read Mara's book on locks and atomics? Hands up, anybody? It's a fantastic book. You guys absolutely should read that. I think it really gives a good baseline on that. So we have a lock. You have a single atomic there and a string, both static. Sorry. And then we have this operation where we do the compare exchange. If the lock is false, then set it to true. We'll use acquire ordering there. And whenever you see acquire, just think there's a release floating around somewhere that you should be thinking about. If it fails, we're only doing the load. We're not doing any swap, so we can do a relaxed load. And if that works, if we acquire the lock, technically, we can now push an exclamation point into the string unsafely. And then after that, we release the lock. So when we release the lock, any changes, remember, anything that happens before it will get pushed into the other threads, will be visible to other threads. That change to data will be visible to the next thread that synchronizes with it. So we have 100 threads that are going to run. Who wants to guess how many exclamation points are printed on with this code? That's just yell a number. Who said one? One, yeah, okay. Any other number here? At least one, yeah. At least one. Yeah, you guys know, yeah, at least one. Sometimes two, depending on your, just know it could be any number, right? Depending on how those threads choose to execute. Here's a diagram just showing that. We have thread one doing the cast. It sets a lock, enters the critical section, closes the lock or sets the lock to false, and then that data, the single exclamation point, works. Another thread can see that once it synchronizes with, it will see the changes done by that release and then add to it, and then set the lock and where it is. In between, you have threads that are attempting to acquire the lock, but they can't, so they just enter a failed state using a relaxed ordering there. You can also get a scenario here, which I think is a little bit more interesting, where thread one is done. Thread one is done. Thread three happens after thread one releases the lock, but it still doesn't see it. And that's a possibility because remember, these changes have to propagate throughout the hardware. So it still has the old value with it, despite thread one being done. So it might not see it. Thread four sees it and then acquires the lock. And so you can't say that you're going to get 100. You can't say with confidence that you could get 100. But you can easily get one as well, or anything in between, depending on how your hardware runs. And so the way to fix this, if you want to make sure you have 100, just loop on the lock, on the compare exchange operation, and ensure that you're now checking that once this is done, all the other threads will keep looping, keep waiting. Once it sees the lock, it'll grab it. The next one, once it sees the lock, it'll grab it. Eventually, you'll get 100 different exclamation points printed out. All right, and last one here is channels. Very popular way of using synchronization. It makes use of sender and receiver types that interact with the channel under the hood. So I want to do a little bit of a dive into channels. Each channel works by, I'm going to focus actually on the bounded one, which is uses, I think it's called a ViewCov ring buffer underneath the hood. I might be blanking on the name there. But each channel uses a slot. And it's within the buffer, it has an array of slots that the channel can write to. and then so you write to the tail and read out from the head. Here are some of the methods that we're used to within channels. You have the receive, send, all those, and some of the helper ones down there. And it's like a diagram I try to draw of what a channel actually does. So when you call send on the right side, what it does is that it will call start send, which basically ensures that there's actually a slot available. And then if there's a slot available, it will write to it. And it will then ask a thread that's waiting to read it, hey, wake up and read whatever's written. And then we'll read that and pull down that message down. And now that message then becomes available through the receive. From a concurrency perspective, there's quite a bit happening, especially in the start send, where we're trying to reserve that slot or check whether the channel is full or disconnected. What we end up seeing is we do a load for the tail, which is like the end, remember we're adding to the back. We do a relaxed load. Now, the reason we're doing a relaxed load, it's cheap, right? And we're also gonna loop and keep asking for load that way. So if you can loop, relax is not a bad way to think about actually loading data. It's a cheap way to do it. We then get the index from, there's some implementation details I had to remove here. We end up extracting the slot, and then we end up loading the values, information from the slot using a load acquire. Remember, when it's acquired, there's a release somewhere. So within that, what we end up seeing is that there are three cases within that if. If the stamp is equal to the tail, we can then say, hey, we've reserved a slot, let's push the tail forward, and then eventually alert a sender or a receiver that we're now writing to it. But the way we push the tail forward is that we do a compare exchange with the actual current value of the tail, and then we try and put in the new value of the tail, and we use sequential consistent ordering. And the reason we're doing that is because, remember, there could be a lot of operations happening on that particular buffer. And we want to ensure that certain things like the head, the tail, the capacity has a global agreed upon order with all threads. And that's why it's important to use a very strong ordering like sequential consistency. If that's the case, and that works, and we're able to swap to the new tail, we'll just set up the token. The token's we end up using to send the data. If not, we'll just back off for a little bit and try again. We'll do another load, this is line 30, of the tail using relaxed. Because we're looping, it's fine if we keep doing it relaxed. You might miss the first time and get the wrong value, but we'll loop again and eventually get the right value. And then there are other scenarios here where that kind of get these intermediate scenarios where, like, what happens if the buffer is actually full, or some race happens where a read is still happening and a write cannot yet reserve a slot. The write method then takes that token that comes from the receive, the previous method I just showed you. It checks if that slot is null. If it is, it errors. The channel could be disconnected. If not, it then gets a slot from the pointer, and then it then writes the data that you provided with it, that message T that came in the function arguments. It writes it into it, and then we now call a release to it, and that now gets released. So another thread will synchronize on that and be able to see that value that then comes in. We then notify a thread to kind of pick up that read later on. Same thing happens with start receive. I won't go through the details. It's the exact same, but now all operations happen on the head side, and still follows the load using relaxed. It does an acquire as well to get the load from the stamp. It tries to push the head as well using sequential consistent ordering, and similar operations will happen on that side. And here's the read method. We just read the value and return the message at the bottom, and you get to see it on the other side of the channel. Yeah, and this is, so yeah, that was an extra slide I had there. But yeah, that's basically it.